So a population is defined as the collection of all data you want information about. A keyword to population is this word all. You want all the data. So if I wanted to know some information about like students here at Papillion La Vista South High School, I want to know how many students are using the vending machine on a daily basis. Okay. If I wanted to survey the population, I would have to speak to every single student in the building and ask them, do you use the vending machine on a daily basis? Okay, then I would be talking to my whole population, all the students in the school. Most often when we talk about statistics, statistics are not generally based on populations. They're based on samples. And the definition of a sample is it's a subset of your population. Okay? So a subset of the population means a small group. Now, statistics will be more reliable if your sample size is larger. Okay, so if I only ask like 10 kids if they're using the vending machine every day, that might not be a good sample for all 1,600 students in our school. Okay, but if I decide to poll my classes, I've got like 120 students, that seems like a reasonable sample size, and then maybe I could project that over to my population. Okay, but if you just talk to a few in a group as opposed to a whole population, that would be like a sample. Okay. The next two definitions are parameter. Parameter is a numerical description of a population characteristics. Please put your phones away. A numerical description of a population characteristic. So it would probably be easy for us, like downstairs in the main office, to look at our entire enrollment for Papillion La Vista South, and we could come up with some parameters for our school population, things like what's the percent of females versus percent males, and we would be accounting for all of the students. So that would represent a parameter, not a statistic. It's an exact numerical characteristic. But there are other things where if I don't use the entire population, it's not a number descriptor like a parameter. It would be more like a statistic in that it's an estimate. So a statistic is defined as a numerical description of a sample characteristic. So this means I'm just looking at a small group. And therefore, it's not an exact value for my entire population. It is an estimate for my population. So if I go back to the example where I start asking students, do you use the vending machines every day? And maybe I poll my classes and I find 30% of my students use the vending machine every day, then I could project that out to all of PLS and say, you know, probably 30% of Papillion La Vista South High School students are using the vending machines every day. Okay. Now, we would understand that that's just a statistic. There could be more students using the vending machine. There could be less students using the vending machine. It's just an estimate, not an exact number. Okay. And then moving right along to hypothesis. You guys know hypothesis from science class. How do you define a hypothesis in science class? Perfect. Someone always says that first. That is the definition. okay, an educated guess. We can think about our hypotheses as educated guesses. We're going to say a hypothesis is a claim about a characteristic of a population. So I could make a claim based on what I see on a daily basis. I could say I would estimate like probably 80% of students at Papillion Limited South have cell phones. And that could be my hypothesis. And then I could do some investigation. That's educated based on what I see in my classroom. I could do some investigation whether I pull the entire population or I just take a sample, a subgroup of the population, and I ask them, like, do you have a cell phone? And then I could see what that statistic number is and then apply it and decide if my hypothesis was valid. Okay. Now, an important thing that we want to at least touch on, we're not going to get too far into this, but if you make a hypothesis, and this is true in science class too, you also want to be able to say, like, is your hypothesis valid or invalid, right? Okay. So we want to be able to distinguish between results that can easily occur by chance in the real world versus results that are highly unlikely to occur. And this is where our probability and statistics come in and play a role. Now you won't have to do much of the work for this second bullet point. This second bullet point will actually be done for you in what is called, and you're going to put this in the notes section of that workbook, something called a simulation. So how will we gather information about what is very likely to occur and what is highly unlikely to occur? We're going to gather our information from simulations, but we're not actually going to run the simulation. The simulation will be run for us, and we'll just get the results of the simulation. Okay. So a simulation is what we're going to use to analyze our hypotheses. And when I say analyze the hypothesis, I mean, is it valid or invalid? Is it true or false? Now, simulations oftentimes are run by computer programs. So technology is a great tool we can use to create simulations. A simulation uses a real-world model with the specific conditions that we would see in the real world, so that the outcomes of the simulation closely match what happens in the real world. You're almost done, Robbie. The rest won't be as much. So an example could be like rolling a die. We know from our studies in probability about theoretical probability of rolling a die and conditions that should happen when you're rolling the die, 1/6 chance for every number. So I could create a simulation, and there are lots of simulations out on the internet for rolling a single die, where I can push a button and I could tell the computer to simulate rolling a die 500 times. And it'll roll the die 500 times, and then it will maybe produce a histogram for me, like how many times it roll a 1, how many times it roll a 2, okay, and it will give me those values, okay. Or like a little bit more advanced, there's lots of statistical software out there. We could put in conditions for what we know about like the spread of a particular disease, like the spread of the flu. And we could put in the conditions into the system, and then it would generate like a simulation of what could happen in terms of the spread of the flu under certain conditions, if people aren't vaccinated, okay, if this happens. And so it would give us like what could happen in the real world under those particular conditions. Okay. But that's a little bit above us, the simulation right now. So remember that the simulation will be done for you, but you will get from the simulation the information that you need to decide if the results easily happen in the real world or are very unlikely. Okay, so in order for us to say if something is true or false, we need to know if it's likely to happen or not likely to happen. Simulations are going to tell us that. The simulation will be run for us. We just have to look at it. I think I have one more thing. If you run the simulation and the results are highly unlikely to happen in the real world, then we can conclude that the hypothesis is probably false. Now, the book and I will make extra efforts to use the word probably or most likely, because there's lots of other statistics that we're not covering. Things like statistical significance and confidence intervals that would help determine if a hypothesis actually is true or false. But we just need to accept the fact that while the simulation may tell us that it's very unlikely to happen in the real world, we could then say that this hypothesis is false, and we could be wrong. So we might conclude something, and we can conclude something that is incorrect. That is possible. So that's the front side, and you got a lot of information there. Like I said, lots of definitions in chapter 11, lots of reading and lots of writing we'll be doing. Okay, we're going to flip open to like page 2, I forget what numbers I'm on, 230, am I in the 30s? 230, no, 222. I think we're going to flip to 222. Is that right? 322. Thank you. 322, and we're going to look at some examples. So I'm going to do example 1, and then I'll give you some time to try out example 2 and 3 on your own. So in example 1, it says, in a city, a survey of 3,257 adults ages 18 and over found that 2,605 of them own a tablet. I want to, in the directions, identify the population and the sample, and then I want to describe the sample. So I'm going to put a P and an S, one for population, one for sample. This is on page 322 if you just flip over those notes. And sometimes I think it's actually easier to decide what your sample is first. Remember, your sample is a subset of your population. So the sample in this particular problem are those 3,257 adults that I'm talking to. So I'm going to put my sample as 3,257 adults, ages 18 plus. Okay. That's who I actually talked to. But I think we could probably agree there's probably more adults in the city than 3,257. So the population is all adults ages 18 plus in the city. This is limiting me to a city. Sometimes it limits you to like the United States. Okay. So I've identified population and sample. The last thing you want to do is describe the sample. So this is very similar to something we did in chapter 10 with our two-way tables. I want to break up this 3,257 into two categories. So to describe my sample, I would say 2,605 owned a tablet. That's given to me. And then I'll use my total sample to figure out that 652 did not. And that's all I have to do to describe my sample. Basically report the findings. So what I would like you to do next is read through 2 and 3 and do the same thing that I just did. List your population, list your sample, describe your sample. We'll put the answers up here in a little bit and you can check them. Okay? As I walked around, I saw a lot of people doing very similar to like what I did on that example, which I think is a great way. Do your sample first. So say what your sample is, and that helps you maybe answer what your population is. So number 2, your sample should have been the 1,000 athletes who were surveyed about the sports drink. Your population is all athletes who drink sports drinks. Okay? And then to summarize your sample, you'd say 726 like the new flavor, while 274 do not. Okay. In number 3, you're working in a school district, so that's going to limit your population. You survey 1,500 high school students, so that's your sample, 1,500 high school students in the district. And then your population is all the high school students in the district. And you would summarize and say 824 have jobs and 676 do not. Okay, so you'll have some questions similar to those in your homework assignment. You got to read it and you got to do 3 things. Decide the population, decide the sample, describe the sample. Okay. Now, the next set of questions starts on number 4 at the bottom of the paper there, and then goes on to the back. It asks a different question. Instead of asking about population and sample, it moves on to the 2 other definitions we gave for parameter and statistic. So it's saying, determine whether the numerical value is a parameter or a statistic, and explain your reasoning. Your reasoning should have something to do with, does it account for all of the people in the population, or are you just sampling a small subgroup of the population? Okay, so let's look at number 4 together. 82% of the residents in one neighborhood in a town voted to approve building a bike lane through the town. Does that represent everybody in the town? Jackson says, no, it's just one set of people in one neighborhood. So this would be an example of a statistic. A parameter requires you to pull a population. Think P goes with P, statistic goes with sample, S goes with S. And we're not pulling everybody, so we are working with a statistic. Now, I could pull that one neighborhood, and I could say then 82% of people in the town approve the bike lane. I could project that out to the whole town, but I haven't actually asked the whole town. Number 5, in science class, 25% of the students wear glasses. Parameter or statistic? What's the population, do you think? What's that? Students in the science class. If the population is the students in the science class, do you think, let's maybe make it Algebra 2 class, do you think we could get a parameter or a statistic for the number of students wearing glasses? Can we count everybody in here? I think we can take care of everybody. If we're including all the people, then it would be a parameter. Okay. So I think the fact that it says in a science class, this is your population. It is very easy for us to get data in a single class. So I would say this is a parameter. All students will be accounted for. So I can do a quick survey right here in Algebra 2. It looks like I have 2 students with glasses. Okay, and that's a parameter in this classroom because it's for everybody. In a recent year, the median household income in the United States was about $52,000. Jacob? Parameter, yeah. It doesn't tell us that we only surveyed a certain number of households, and we should be able to collect data, like through taxes and things like that, where we could calculate, we know the income of all the households in the country, so we would be able to do that for everybody. That would be a parameter. And then 7, a survey of some of the visitors to a museum said that they thought the planetarium was exciting. This would be statistic, keyword, Sahil? Some. Just some of the visitors. So we're not asking all of the visitors if they like the planetarium. It's only a group of them. Okay. Now, we're running low on time, so I'm not going to do the last example. We might do that at the very beginning of class tomorrow.